confirmation yet. Nothing received yet, and that was at 10:57.
What was his name?
He's my brother. He's got the same last name. First name is Raed. Raed. I don't think. I see him now. I see him. Okay, he's there.
Okay, good.
Okay.
Okay. All right. Sorry for that brief delay, everyone. Thank you for joining us today. Make sure that I'm recording. Yes, I am. Okay, fabulous. All right. My name's Kara. I am the Partnership and Communications Coordinator for ECU Center for Sustainable Energy and Environmental Engineering. I'd like to welcome everyone today to our webinar, Reducing the Carbon Footprint in Manufacturing Facilities. The mission of our center is to promote renewable energy technology and natural resource conservation through scholarly and applied research in an effort to enhance industry awareness and best serve North Carolina communities. With research funding through the EPA's Pollution Prevention and Source Reduction Assistance programs, center students, faculty, and affiliates provide valuable resources to businesses and industries across North Carolina. We offer energy, P2, and lean assessments and training largely to North Carolina automotive, chemical, fabrication, and food and beverage manufacturers. After conducting a facility assessment, the center additionally provides technical feedback and various business analyses. We also facilitate certification workshops like Lean Six Sigma for sustainable and green manufacturing. So before I introduce today's speakers, just a little bit of housekeeping. We're recording today's event. Access to the event will be provided by email concluding today's webinar. We encourage you to interact with our speaker. We'll be taking questions at the conclusion of the presentation, or you can just drop your question in the chat box at any time, and I will ask for you at the end of the presentation. In the follow-up email, I will provide a link where you can take a moment to give us any feedback on how we can improve future events. And then finally, the email will also provide a link for donating to the center, or you can just simply go to give.ecu.edu/CSE3 at any time, and we truly appreciate any contribution as it helps us to support student activities and community engagement. So with that, today we have Dr. S.A. Sherif. He's a professor of mechanical and aerospace engineering and the director of both the Industrial Assessment Center and Mobile Energy Laboratory at the University of Florida. He also served as co-director of the Southeastern Center for Industrial Engineering Intensity Reduction at the University of Florida from 2009 to 2013. He's a Life Fellow of the American Society of Mechanical Engineering and American Society of Heating, Refrigeration, and Air Conditioning Engineers, a Fellow of the Royal Aeronautical Society, an Associate Fellow of the American Institute of Aeronautics and Astronautics, the Vice President of Commission B2 on Refrigerating Equipment of the International Institute of Refrigeration, a member of the Advisory Board of Directors of the International Association for Hydrogen Energy, a founding member of the Board of Directors of the American Society of Thermal and Fluids Engineers, and head of the refrigeration section of the ASHRAE from 2004 to 2008. Dr. Sherif currently serves as editor-in-chief of the ASME Journal of Solar Energy Engineering, and he also served as editor-in-chief for the Journal of Thermal Science and Engineering Applications from 2014 to 2019. He is on the editorial boards of 22 other thermal science journals, and he has written more than 300 papers, 1 book, 20 bound volumes, 24 chapters, 200 technical reports, and 2 U.S. patents. So I think it's safe to say his credentials check. So thank you so much, Dr. Sherif, for your time today. I will turn the platform over to you.
Thank you very much, and I would like to express my sincere gratitude to both of you for inviting me to be the speaker today. It's my pleasure to be with you. I would like to share my screen with you, and let's see if I can get to do that. And I'm not seeing the share link here. Yeah, here it is. Okay, so let's see. It's taking time to just get the file up. Okay, I hope you can see the screen.
We can.
The title of the presentation is Assessment Recommendations and Best Practices for Improving Energy Efficiency and Reducing the Carbon Footprint in Manufacturing Facilities. The outline of my presentation is going to cover the Industrial Assessment Center program as part of the U.S. Department of Energy. I'm going to talk about energy efficiency and carbon footprint, best practices versus recommendations, or what we call assessment recommendations, which is going to include a whole host of areas that include lighting, motors, compressed air systems, heating, ventilating, and air conditioning systems, boilers, waste heat recovery systems, some renewable energy utilization, although I'm going to be light on that for now because of the time, and combined heat and power and on-site generation. And then I'm going to show you the summary table that we typically leave with the client in our reports. We produce these reports. About 20 of those reports we produce every 12 months. And every one of them represents a client that we have actually assessed, or if you like to call, audited it, in terms of their energy efficiency, their productivity improvements, their waste management activities, their cybersecurity. We talk about Internet of Things, the SCADA systems, and a whole host of other things, but primarily the energy efficiency, waste heat recovery, and productivity improvements are the three big items that we basically work on. This is the map of the industrial assessment centers in the 2022-2026 funding cycle, which started September 1 this last year. We are at the University of Florida, in fact, one of two centers in the state of Florida. The other center is at the University of Miami in Coral Gables, and they are in charge of the southern half of the state, if you like to think of it from south of Orlando, perhaps going from Sarasota all the way to Dade County and Broward County and Palm Beach County, Port St. Lucie, all these locations in South Florida they're in charge of, and then we're basically in charge of the central, north central, and the panhandle areas of the state of Florida. There are a total of 31 centers in the United States in the new funding cycle. There are some satellite centers that are not fully, they're sort of under the auspices of other existing centers. There's one in, I believe, in Puerto Rico, and so you can see it concentrated in the Northeast and in the Midwest and the Southeast, and then of course in the Western states and the Rocky Mountain states there are fewer centers, primarily because of the nature of the states there and the vast land mass that exists and the smaller population centers that exist in these states. This program has been established in 1976 under the so-called Energy Analysis and Diagnostic Center program. That lasted for a good while, and then at that point they were focused primarily on energy, and then they expanded the mandate of the program to include energy, to include productivity and waste management, and they called it the industrial assessment centers, which is a more broad term to include non-energy activities. And we have been funded since 1991. The center has been in existence since 1991. We primarily do energy assessments to mid-sized manufacturing facilities in Florida. We used to work in southern Alabama and Mississippi, southern Mississippi and southern Georgia as well. And we still do some of those, but we try to focus more on Florida. But we have been in these areas, and we have done some assessments there as well. This slide shows you the interaction among the different entities in the IAC program. The federal government, of course, provides the money basically to universities. These universities take the money and fund the faculty, fund the students. The faculty teach the students. Part of our mandate is to educate 10 students every 12 months to be certified in energy engineering, and they get certification from the U.S. Department of Energy when they finish that certification. So we have two things that we get graded on: our assessments to the manufacturing facilities. We need to do 20 of those per year or per funding cycle, and then we need to do 10 students every year that would be certified for the program. Certified Industrial Assessment Center student lead, or lead students, if you like. This is going to help the workforce, produce qualified engineering students who are able to work in energy, and at the same time, they help the manufacturing facilities. You can see the arrow down from the students to the manufacturers, and of course, the faculty work with the students, and the manufacturers help us because they also give us ideas about the different real engineering problems that exist, and we work with them. So a lot of the problems we work on are real life engineering problems. And of course, all of that leads to success, job growth, higher taxes. So it helps everything in a very nice way. Now, I'm going to focus more on Florida and the Florida industry, since this is what we are here for. In the Florida industry, you can see that these are the big ticket items here. And it might be surprise to a lot of us that the motors and pumps are about 50% of the electricity usage in manufacturing facilities. Then you have lighting, you have air conditioning and chillers, about 15%. Air compressors at about 15%, and then there are other things that would be in the form of 10% of the total pie chart. So the way I'm going to do this presentation is I'm going to walk you through examples of how to compute the energy savings. First, identify these energy savings, and then tell you how we're going to do it. We have about close to 300 different templates for what we call assessment recommendations, or ARs. These assessment recommendations we have developed over the many years. Since 1991, we've had the templates created. We create new templates as we develop new ideas, and I'm going to just show you maybe 6 or 7 or 8 of them today, so that you can get an idea of how it works. So for illustration purposes, I have used some numbers for the electricity cost. I used 5 cents per kilowatt hour. The natural gas cost, I used $2 per million BTUs. The demand cost, which is the utility companies will charge the manufacturing facilities for demand, meaning that if you hit a certain magic marker as far as your demand, they will charge you. There will be a surcharge for that. So that's about $6 per kilowatt month. or kilowatt per month, if you like. Workers' wage is about $20 an hour because when it comes to productivity, we're going to need the workers' wage to be able to assess how much improvement in productivity or how much money we can save by improving the productivity. So here, these are the quantities that we're going to compute. The energy savings, and that's kilowatt hour per year. The demand reduction, which is going to be in kilowatt per month. And every kilowatt we reduce, we're going to save $6. Thermal energy savings in million BTUs per year. Cost savings in dollars per year. The carbon dioxide reduction, which is going to be in tons of carbon dioxide per year, which that would impact the so-called carbon footprint. And then the simple payback period, which is going to be how many years it takes for the facility to recover the money that they have invested in implementing the improvement that we have recommended. And then the return on the investment, which is really the reciprocal of the simple payback multiplied by 100. So it's the cost savings divided by the implementation cost multiplied by 100. And then the carbon dioxide reduction, we use the Environmental Protection Agency. For each state, the EPA provides a number that you can use. And for the state of Florida, it's 0.5322 tons of carbon dioxide per 1,000 kilowatt hour. So every 1,000 kilowatt hour or megawatt hour, if you like, would save you about half a ton of carbon dioxide that would have been discharged to the environment. And of course, the implementation cost, we rely on the existing vendors. We contact these vendors. We are not allowed to recommend any vendor, but we do get the information from these vendors in terms of how much a certain piece of equipment would cost, or a certain sensor that perhaps the facility would want to buy to, let's say, detect the leak, the air leaks from the air compressors and so forth. So one of the recommendations that we do is lighting, install high efficiency lighting. So let us take an example of a facility, manufacturing plant that has 20 lamps. It has, each lamp is a one bulb lamp, meaning that it has one bulb, and that bulb is a 400 watt light bulb. The ballast factor is 1.15. Again, I'm giving examples here from, these are actually numbers from a real facility. Each bulb is going to provide 3,500 lumens of illumination, and it's on all year long. So the assumption is that we're going to leave it on all year. That's 365 days, 24 hours a day. So what we do is we recommend to change these for their equivalent 110 watt LED bulb. The LED bulb is a more efficient light bulb. It has a ballast factor of 1. It provides the same amount of illumination, but of course it's 110 watt instead of 400 watts. The cost of a 110 watt LED bulb is $223 per bulb. So it's not cheap, but hopefully you will be able to recover the cost over time. The demand reduction in this case, since you have 20 of those, would be computed as 400 watts, which is the wattage of the bulb, multiplied by the ballast factor. Then you subtract from that the 110 watt multiplied by the ballast factor for the new bulb that you're going to install, the LED bulb, and then you multiply that by the conversion from kilowatt to from watt to kilowatt, and then you get 7 kilowatt for the demand. The demand reduction is 7 kilowatt, which is going to translate into energy savings of 7 times the number of hours per year, which is 8,760 hours. You're going to get about 61,300 kilowatt hour per year of energy savings. But when you compute the cost savings that you're going to achieve, you're gonna factor in the demand cost, which now you're paying $6 per kilowatt for the demand. So if you save 7 kilowatt, that means that you're going to save 7 times 6, and then you multiply that by 12 months per year. And then you add that to the savings that you achieve from the 61,320 kilowatt hour per year that you are no longer expending, times the cost of energy at this, which is $0.05 per kilowatt hour, and you end up with $3,570 per year of savings. And if you convert that into CO2 reduction, you multiply by the multiplier from the Environmental Protection Agency for Florida, and you end up with 32.6 tons of carbon dioxide per year that would have been discharged otherwise. The payback period is basically you divide the 20 times the cost of the bulb, so that's going to be the money that you're going to pay. You divide that by the savings, and you end up with 1.27 years. So you should be able to recover your money in 1.27 years. And the return on the investment, if you take the reciprocal of the 1.27 and multiply the reciprocal by 100, you get 79.92% of return on your investment. So that's an example. We have a lot of those templates. Like I said, this is quick summary of how we compute the lighting savings. And I'm going to take you to another one right now, which is motors. And of course, you saw that motors are 50%. Motors and pumps are 50% of the electric consumption in manufacturing facilities. So here, what we do is we replace. We have to make a decision as to whether we should rewind the failed motor or buy a new high premium, or what we call a premium efficiency motor, or a high efficiency motor. The difference between a high efficiency motor and a premium efficiency motor is a very small increase in the efficiency. I believe 96% for the premium efficiency, 95% of a high efficiency. Now, if you rewind the motor, the downside is that your efficiency will get reduced by 3 to 5%. Every time you rewind a failed motor, you're going to lose 3 to 5% of the motor efficiency. That's the Oak Ridge National Lab, which is the source for those of you that would like to dig this up. So as an illustration, we're going to take a 50 horsepower standard motor, let us say, with an efficiency of 78%, and that will be replaced by a premium efficiency or a high efficiency motor. In this case, I'm just going to use the two words interchangeably. It was 95% efficiency. Now, assuming that the motor is going to work at an 80% load factor, by the way, the load factor is defined as the ratio between the measured amps. You can get an amp meter and measure the amperage across the motor windings and divide that by the rated amps on the nameplate for the motor, and you will get a ratio, but or a percentage, depending on whether you multiply it by 100, 0.8 or 80%. And as we're going to assume that's going to run for 7,000 hours per year. So that's not quite the 8760 hours per year. So 7,000 hours that you're going to shut these motors a little bit. In this case, the demand reduction would be is 50 horsepower. You convert that into kilowatt by the multiplier is 0.746 kilowatt per horsepower. You multiply that by the efficiency of the motor. I'm sorry, it was by the load factor, by the 80%, which is the load factor. And then you multiply that by 1 over the efficiency of the old motor minus 1 over the efficiency of the new motor. And you're going to find that that's going to produce 6.85 kilowatt of demand reduction. And that will translate into, you multiply that by $6 per kilowatt, correct? So you're going to have that savings. And then the energy savings are going to be the demand reduction multiplied by the number of hours that you ran the motors, which is going to be 7,000 hours per year. You end up with 47,950 kilowatt hour per year of savings. And then you add the two together. You're going to take the demand savings, which is 6.85 times $6 times 12 months, plus the 47,950 multiplied by the cost of electricity, which is 5 cents per kilowatt hour. You'll end up with $2,891 per year of savings. And the CO2 reduction corresponding to it, again, multiply by 0.5322, you get 25.52 tons of CO2 per year. Now, if you compute the payback, you get the cost of the high efficiency motor minus the cost of the rewound motor divided by the cost savings, and you'll end up with 0.42 years. And the return on the investment, you get the reciprocal of 0.42 multiplied by 100. You get 238.1% per year. And you can, for the cost of the motor, you can go to Grainger.com, for example. That's one site where you can get some of these motors priced up for you. Okay, we're going to move on to the next assessment recommendation possibility, which is use of variable frequency drives. These variable frequency drives are used to reduce the speed of a certain motor in order to reduce its capacity momentarily. In other words, you don't need the full load. You're operating sometimes on full load conditions, sometimes on part load conditions. So if you're operating on part load conditions, if you have a mechanism that would reduce the speed of the motor when you are not needing the full power of the motor, that would save you some money. In order for you to do that, you're going to have to automate this process. And in order to do that, you're going to have a drive controller that's going to interact with the drive motor, and then have a mechanism where the controller can make decisions, perhaps use a programmable logic controller as a feedback loop, and so that you will be able to do that and get the speed of the motor reduced as needed, or increased when you need more power by the motor. So that's sort of how it works. By the way, the cost of a variable frequency drive, if you have a 100 horsepower motor, you're looking at about $3,200 of variable frequency drive cost. So again, it's not cheap, but if you have a whole bunch of those, you're going to have to spend a whole bunch of money on that. Now, if you look at the way we're going to calculate the savings, again, we're going to use a 100 horsepower standard motor with an efficiency of 80%. It's working at an electric load factor of 75%. Again, the load factor is the ratio between the amperage you measure across the motor windings divided by the nameplate amperage. If the motor needs to run at 10% less speed than usual, let us say that it wants to run 10% less speed for about 1,500 hours of the year. So if you install a variable frequency drive, that would probably help you. The question is, what will be the energy and cost savings associated with installing such a variable frequency drive? If you use the affinity laws, if you like those, we call it the affinity laws, with in this case the cube law, which is the horsepower over the horsepower is proportional to the RPM over the RPM cube. So the horsepower for the final condition equals the horsepower in the initial condition multiplied by the RPM for the final over the RPM for the initial, all raised to the power 3. So if we reduce the speed by 10%, that means that the RPM for the final is going to be 1 minus 0.1 multiplied by the RPM initial. So you'll end up with 0.9 times the RPM initial, which is whatever it is. If you cube it, you're going to end up with 0.729 multiplier, which is going to reduce the 100 horsepower motor rating to 72.9 horsepower. And as a consequence, your energy savings is going to be the difference in horsepower multiplied by the load factor, multiplied by the conversion from horsepower to kilowatt, multiplied by the number of hours, divided by the efficiency. And if you do all that, you're going to get about 28,430 kilowatt hour per year. Here again, I'm listing for all of you that the load factor is the ratio between the measured amps divided by the amps on the motor nameplate multiplied by 100. In this case, there are no demand savings, even though you reduce the demand, because you have not really replaced the motor. So the motor is still there, same motor. The carbon dioxide reduction, of course, can be calculated as usual, multiplying it by 0.5322. All right, so that's again another possibility, which is the variable frequency drive. This is how it looks. It costs about $3,200 installed. That's including the installation cost. In this case, the cost savings will be the amount of energy that you save, the 28,430 per kilowatt hour per year. You multiply it by the cost of energy, $0.05 per kilowatt hour. You end up with $1,478 per year. If you put the implementation cost at $3,200, you're going to end up with a payback period of $3,200 divided by 1478. You get 2.17 years. And again, the return on investment, you take the reciprocal of the payback period multiplied by 100, you get 46% return. Let's go to the next one, which is air compressors. if you consider, again, as an example, a 100 horsepower compressor, let us say that it's running 3,000 hours per year. It's generating compressed air at 120 psi, that's pounds per square inch. Now we go there and we realize that these guys don't really need 120 psi. They need 90 psi. They are over working their compressors without really having a legitimate need. So we identify the need, and then we say, all right, you guys need 90 psi, but we're going to give you 100 psi to allow for losses in the lines and for any possible air leaks. So now they're no longer running the compressor to produce 120 psi compressed air, but 100 psi compressed air. And if you look up what Oak Ridge National Lab recommends, they say for every psi that you reduce in the pressure in the line, you save 0.5% of the energy used by the compressed air system. So in this case, now we have saved them 20 psi. So we take the 20 psi, multiplied by 0.5%, and we end up with 10% of the energy used by the compressor as savings. Now, if you assume that the load factor here, we're going to make a simplification. We're going to assume that the load factor and the efficiency have the same value, like let's say 80% for each, only so that they can cancel. And you don't really have to make that assumption. You can plug them in, and your equation will be just fine. If you look at the equation down below that statement, you will see that it has the load factor and it has the efficiency, the LF and the EFF. So if you cancel LF and EFF, you get to the next line, which is the 0.1, which is the savings that you had, the 0.1, the 10%. You multiply it by 100 horsepower, convert it into kilowatt hour, the multiplier 0.746 by 3,000 hours per year, you end up with 22,380 kilowatt hour per year of savings. Your cost, that would be that number multiplied by 5 cents per kilowatt hour, $1,119. The CO2 reduction would be multiplying it by 0.5322, dividing by 1,000, you get 25.5 tons of CO2 per year. And the payback here is actually immediate, because you really haven't done anything. You haven't purchased anything. So therefore, you haven't invested any money in it. It's a low-hanging fruit. The payback period is immediate, and the return on investment does not apply in this case. Doesn't have any physical meaning, because you haven't invested anything. Now, the next one is installing what we call HVLS fans, which are the high-volume, low-speed fans. And this is a picture of what they look like on the left side, and the right picture showed you one in one of the actual facilities that we've audited. These are revolving fans. They revolve slowly. The fan pushes a wide cylindrical column of air that produces a horizontal floor jet after reaching the ground. So you've got this big, huge horizontal floor jet. This wall of air spreads in all directions, a 360-degree direction, away from the center of the fan. The depth of the floor jet is determined by the velocity of the downward moving air and by the diameter of the fan. These fans can lower the temperature on the floor by up to 15 degrees Fahrenheit, anywhere from 5 to 15 degrees Fahrenheit, simply because of the so-called wind chill effect. So you haven't done any air conditioning here. You haven't spent any money on an air conditioning system, but just simply using these high volume, low speed fans, you can actually achieve a 5 to 15 degree reduction in temperature. Now, the question now becomes, how do we convert that into productivity savings? Or shall we say productivity improvement? So these savings that are generated by an increase in productivity in a given area is going to be illustrated by let's take 5 workers in a certain area of the manufacturing facility, and let us say, for the sake of discussion, that the temperature has been reduced by 7 degrees. We took the middle road. Instead of 5 and 15, we took 7. The plant is running 24 hours a day, 5 days a week, and 52 weeks per year. We're going to show you in this illustration how we translate that into dollars and cents. It's well documented that the productivity falls by 2% per degree temperature rise. This is known, and we have cited a source for that. That translates into 2%, translates into 14% increase in productivity per hour of work, or in this case, 8.4 minutes per hour. And therefore, if you want to compute the cost savings, it would be the productivity increase minus the energy that has been used to run these high volume, low speed fans. The productivity increase, we call it PI, productivity increase, is the number of workers, which is 5, multiplied by the labor cost, which is $20 per hour per worker, multiplied by the number of hours that we have recovered or saved, is 8.4 minutes per 60 minutes. We have 5 hours per day, 5 days per week, 52 weeks per year. And I'm seeing here that perhaps we should have 24 hours per day instead of 5. So I'm going to check this number, after the presentation. And we got $18,200 per year. Here we got the E, which is the cost of energy. The energy first. Let's compute the amount of energy. You're going to take the 2 of them. There are 2 fans, so 2 times 2 horsepower fans. The efficiency of the fan is 85%. You convert it into kilowatt by multiply 0.746, and then here you're going to multiply that by the number of hours per year times the cost of energy plus the demand savings that you have, or the demand that would be associated with this kilowatt, which is going to be multiplied by $6 per kilowatt times 12 months, and then you're going to end up with the 1360 plus the 253, which is going to give you 1613, and therefore the cost savings will be the productivity improvement minus the energy expended, and you end up with $16,587 per year. And the implementation cost for per fan is $6,250 per fan. So you're looking at $12,500 for the 2 fans. That's installed cost, and including the installation. And the payback period would be the same as we did before. You divide the 12,500 by the 16,587, and you end up with 3/4 of a year. And the return on investment would be 132%. Another one is installing turbulators in the boilers. And these turbulators are basically flanges inside the boiler pipes. It allows for a better heat transfer that increases the efficiency of the boiler. In other words, you make the flow turbulent, so you disturb the flow, and as a consequence, you end up with a higher heat transfer coefficient and a higher heat transfer rate. If you consider a boiler that uses, let's say, 20,000 million BTUs per year of heat, let's say from natural gas, with a 78% efficiency, if you install these turbulators in the boiler pipes, the boiler efficiency will increase to 83%. You can check these 2 sources. I gave you 2 websites here to justify the increase from 78% to 83%. The energy savings will be calculated, therefore, as the thermal energy that you saved multiplied by the thermal energy that you need, 20,000 million BTUs per year. You're going to put into that boiler, multiplied by 1 minus the efficiency of the current efficiency divided by the new efficiency. So 78% divided by 83%, you save 1,204 million BTUs per year, and that is equivalent to saving $2. Now this is natural gas. The natural gas costs $2 per million BTUs, so you're looking at $2,410 per year. The implementation cost, you've got 250 flanges. It's $15 per flange, so you're looking at $3,750 for the installation, the implementation cost. If you assume that you have 250 flanges, each one is $15, you can justify the $3,750, And then the payback period will be to divide the 3750 by the 2420, and you get 1.55 years. You take the reciprocal, multiply by 100, you get 64.5%. This is another assessment recommendation that is associated with boilers, but in this case, we're going to preheat the combustion air that's going into the boiler. Of course, in the boiler, you are burning a fuel, and in the process of burning the fuel, you have to provide air, which has oxygen in it. That air is cold. I mean, that air is coming from the ambient, and it's pretty, much cooler than the temperature that the air is going to eventually achieve. Now, if you can preheat that air, you can actually save quite a bit. Now, here is an here's a picture of what our infrared camera is showing, and you will see that there's a temperature of 218.3 degrees Fahrenheit that is existing at the surface of the boiler, or 318 rather, and that tells you that is the ideal temperature that the air should be preheated to. In other words, we could get to that point without violating the second law of thermodynamics, if you like to think of it that way. Of course, we're burning methane. This is the chemical energy, the chemical equation for that. You produce carbon dioxide and water vapor and energy. It's an exothermic reaction that releases heat. So in the boiler, the released heat from its exhaust flue gases, what you do is you do a heat exchanger on top of that boiler, and basically you get the air to shake hands with the flue gases. So you're preheating the air from energy that's already going to go to waste. So if you assume that the temperature of the outside air is T1 and that you want to get it up to a T2, and you're looking at possible 315 degrees Fahrenheit. If you look at the next slide, you could come up with what they call a transfer efficiency, or a temperature transfer efficiency. Can be calculated by this ratio, T2 minus T1 over T3 minus T1, T3 being the temperature of the flue gases before the heat exchanger. And you can, a conservative estimate for that ratio is somewhere between 60% and 85%, or 0.6 to 0.85. We're going to use the lower end, which is 0.6. And if that happens, then we can get the T2, which is the temperature of the air at the inlet after the heat exchanger, can be up to 229, up to from the ambient temperature, which is 95 degrees. And as a consequence, you will end up with, if you go to the next slide, it will show you how to calculate the energy savings. If you take that mass flow rate times the specific heat times delta T, and the mass flow rate, of course, is M. The Cp is the specific heat. Delta T is the temperature change. You can compute a percentage of energy savings, which is the energy consumption of the existing system minus the energy consumption of the new system divided by the energy consumption of the existing system. And if you translate that into symbolic form, you get the equation that delta E over E old equals whatever it is here. I don't want to spend my time reading it for you. We simplify the terms, and you end up with the percentage energy savings because the M and the Cp are the same in the numerator and the denominator, so they cancel out. You end up with a T final minus T initial old minus T final minus T initial new divided by T final minus T initial old. And that is where the fuel air temperature is the inlet temperature of the fresh air, and the old and the new is the current system. The old is the current system, and the new is the system with the heat exchange. And therefore, you can get the percentage energy savings translated into, when you plug the numbers, you get 13.2%. This means that using the heat exchanger, we can save about 13.2% of the natural gas consumption in the boilers. If the boiler uses, let's say, 34,159 million BTUs per year, then the annual energy savings for two boilers, in this case, we assumed we have two boilers, consider the efficiency of the heat exchanger being 60%, you can actually compute it, and you end up with 2,705 million BTUs per year was the cost savings. When you multiply by $2 per million BTUs for natural gas, you get $5,411 per year. And the implementation cost would be the cost of the heat exchanger plus the labor cost associated with installing the heat exchanger. We can figure 2 times $7,180 per heat exchanger plus $640 for labor. And we can get the payback period by dividing the cost, the total cost, which is $15,000, by the $5,411 per year of savings that we had, 2.77 years. And then the return on investment, you take the reciprocal of 2.77, multiply by 100, you get 36%. So that's one other thing that can be done. And I believe this is the last one. And I hope that I'm running 46 minutes here, I think, or so I need to wrap things up here quickly. This is the combined heat and power system. In a combined heat and power system, it allows you the facility the ability to generate its own power from existing waste heat sources that are in the facility. So here we use an example of a system where you have a fuel that's running a gas turbine. That's, let's say, natural gas that's running a gas turbine. It's connected to an electric generator that provide power. At their 35%, the thermal efficiency would be about 35% of the energy provided to the fuel, or by the fuel in this case. This power will be used for a certain number of hours. We're going to call it H. It's going to provide electric energy in kilowatt hour per year. And at the same time, the turbine is going to run at about 40% of the energy from the fuel is going to be lost as heat, which can be recovered in a waste heat boiler. And we assume that the waste heat boiler has an efficiency of 80%. And therefore, you will end up with about 32% of the energy from the fuel can, in fact, be used to satisfy the thermal load. And from assuming that from the fuel used, about 25% of its energy will be lost to the environment, then we can go to the next slide and we can see how the calculations are done. You got the thermal load, which is 27,327 million BTUs per year. You divide it by 40% by 80% to get the amount of energy that is going to be needed by the fuel. The heat from the turbine is going to be 40% of that amount, which is 40% of 85,000. You get 34,000. The electricity produced is going to be 35% of that number, which is 85,000. You have to have the conversion factors, of course, to convert it into kilowatt hour per year. You end up with 8.76 times 10 to the 6 kilowatt hour per year. And then the power in megawatt that would be required would be the electricity produced divided by the number of hours, so that you can get it in megawatt from megawatt hour per year into megawatt per year, if you like, megawatt. And you will end up with 1 megawatt. We just got lucky on that. And the losses are going to be computed as 25% of the fuel energy, and that's going to give you about 21,000 million BTUs per year. So in summary, what we have done is we have reduced the demand reduction by 1 megawatt, which is 1,000 kilowatt. That's 1,000 multiplied by $6 of savings. The energy savings are huge, 8.76 times 10 to the 6 kilowatt hour per year. The natural gas savings are going to therefore translate into the fuel energy minus the heat for boiler. You'll end up with about 51,000 million BTUs per year of energy from a natural gas that you don't have to burn anymore. The size of the turbine, in accordance, therefore, is going to be able to generate 1 megawatt. You're going to have to buy a 1 megawatt turbine, and that's going to cost you it's going to cost you $1.4 million per megawatt. So if you have a 1 megawatt turbine, you're going to need to spend $1.4 million. It's pretty expensive, and many facilities shy away from doing it. But the cost savings are going to be the demand savings plus the energy savings minus the fuel, minus the maintenance, you end up with about $302,000 of savings every year. There is no carbon dioxide reduction associated with this AR, and the power used before will now be generated, because there's the same energy and power used before will now be generated. The payback period, implementation cost divided by the cost savings, return on investment as before. The maintenance cost has to be factored in, which is about 12 cents per kilowatt hour. This is the Environmental Protection Agency recommend that number. And again, the 1.4 million per 1 megawatt for the cost of the turbine. So we provide the summary table to the facility that kind of looks like this. We give them the idea that was proposed. We give them the potential savings in dollars per year, the implementation cost in dollars, a simple payback period of how much time it's going to take for them to recover it, return on investment, the energy savings, and the demand savings, and the CO2 reduction. They get a table like that, and then they make a decision as to what to implement. We communicate with them 6 to 9 months after the visit, and we report what has been implemented, and we upload another report to the website, the Rutgers University website, which has the full database for the Department of Energy, all the Energy Industrial Assessment Center program data. So with this, I would like to conclude. I want to thank you for your time, and I'm happy to answer your questions.
Thank you so much, Dr. Sherif. Let's see here. And my screen disappeared. Sorry about that, y'all. Technology, right? So we had a couple of questions in the chat box. There we go. Let's see here. Gary Jones would like to know if you have ever conducted an assessment of a printing operation, and if so, are the results available to the public?
I'm going to have to say yes, but I do not remember doing one in the recent past. But out of the 576 assessments we've done over the years, I'm willing to bet that we did one. I'm going to have to dig up our numbers and check with Dr. Cardenas, who is the assistant director of the center, and he has access to that. I'd be happy to get back to the questioner and answer that. We're going to dig up and see if we have it, and then maybe I can share it with you, and then you can share it with
right.
the questioner.
I just made a little note about that, Gary, just to follow up on that. And then we also have some others that are interested in your presentation. Yes, we will make this available in a PDF format later on this afternoon, or possibly at the beginning of tomorrow in the follow-up email. Richard Harrison just jumped in and said, I found it interesting that lean tools are used for this subject. How are they specifically used?
Okay, I would like to ask first what lean tools mean, so that I can be more pointed in my answer.
Richard, if you'd like to unmute or just type it out in the chat. Okay, so while we're waiting for Richard, are there any other questions that we could bounce to? And Richard's asking for a moment. Okay. Another question, is there a searchable database for all the 500 assessments you've completed?
Right. Absolutely. We do. It's if you Google IAC University, if you just type IAC space university, you will come up with the Rutgers database. You will see the Rutgers database being one of the results of the search, and it will have all the data. I'm not sure whether the data are available to to everybody, but or is it available behind a password protected system? I do not know the answer to that, but yes, there is a database. It's a DOE database that's available, and you should be able to access that database, I believe.
Awesome. Okay, I think, Richard, you can unmute yourself now. I do apologize, everyone. I didn't realize I had you all restricted on that.
It's okay. Can you hear me?
Yes.
Okay, thank you. I know I was starting to do it, and I was like, I can't. And then I realized that's okay. In the very beginning of the presentation, one of the things that was mentioned was using Lean to be able to solve some of the problems, and then going into our presentation with the recommendations and best practices. We use Lean quite a bit in industry and everything, and I never thought about it before. That's what intrigued me, even hearing everything that you talked about, and some very good information. So thank you on that note. But it did get me thinking that yes, lean tools can be used in pinpointing some of what is mentioned, that where we're using excessive or waste that's in there. So I was just curious how you determine kind of specifically to pinpoint those items. Do you use those lean tools, or what other methods do you say these are critical points that we want to eliminate the waste?
Yeah.
Does that make it a little bit clearer?
Yeah, I think I understand your question. I'm going to tell you this: that I never cease to be amazed as to how clever our teams are, and we go in by 1 o'clock in the afternoon. We go in at 8 o'clock in the morning, talk to the engineer at the facility. They take us for a tour. We go to lunch at 12 o'clock. By 1 o'clock, we come back with a long list of things that need to be done. By 4:30 in the afternoon, we are meeting with the facilities engineer, and we're telling them what we're going to do, and we get from them ratings out of a scale of 1 to 5. 5 being that they really are interested. 1, they're not interested. And on the basis of that, we come up with a bunch of things. I just signed a report about a week ago that had 16 recommendations. Okay, now we may start with 25, 30 of them, and then we down select to. This was one of the larger ones. At 16 was pretty exhaustive. It was about 150 pages, 168 pages to be exact. Because it was painful to just go through it, to read through it. But yes, we have the ability. Our team has the ability to go in and within a span of 5 or 6 hours to come up with a long list of things to do. I'm happy to report that our center has been ranked the #1 center in the United States in identifying opportunities, and the second best center in implementing these opportunities. Okay, so we have been consistently ranked very high in identifying ideas, and second best high in implementing these ideas. So I'm very pleased about that. But it's very hard to do in one day. Okay, sometimes we come back for another day, but by lunchtime we normally have pretty much figured out what needs to be done. It is pretty amazing. Even I get, I'm still, trying to figure out how, because it is very hard to go to a facility, haven't seen it before. Of course, we collect a lot of data ahead of time, so we study the facility before we go. But nevertheless, it is a challenge. But of course, the tools that we use are, the toolbox we have is not huge. We have an air leak detector for the compressed air, and we have ultra, infrared camera and all. We have some things, different measuring tools that we use, but all of that combined with experience, and then we come up with something.
Right.
Okay, thank you.
So we are officially at noon. We do have some more questions in the chat. I will happily continue asking these questions if Dr. Sherif is available to answer. And if you need to leave us, that's totally fine. If you'd like to stay for these questions, that's fine as well. We appreciate you staying. So the next question is from, I believe, your brother, the other Dr. Sherif. How do renewable energy generation such as photovoltaic, I think I'm saying that right, compare relative to energy efficiency measures? Do you still get favorable numbers for payback and such?
Yeah, yes, we do. And in fact, photovoltaic is one of our most favorite and most used recommendation. I didn't include it here for lack of time, but using photovoltaics is it's pretty common. We do it almost in every case. So it's very popular. There's no concentrated solar power that we do or anything, but it's mostly the good old-fashioned photovoltaic systems that we put on the roof. And there was one case that not part of the industrial assessment center, but where we did put photovoltaics in the Turkey Lake Service Plaza on the Turnpike. I'm tempted to say about 10 years ago, maybe. We worked on a project for the Department of Transportation where we did quite a bit of that for that Turkey Lake Service Plaza. Okay, but for manufacturing facilities, we do that quite frequently.
Okay. Then we have several comments here from Lampros. I think I'm saying that right. The website at Rutgers has Rutgers has 165 assessments and states that Rutgers is no longer an active assessment center. Where are the rest of your 300 plus assessments? And also mentioned having a cost charge to the facility, or are they free?
It's totally free. There's no charge whatsoever. The Department of Energy pays us, and we do the service. So it's completely free, but you have to qualify for it. You have to have a minimum energy consumption per month of a certain amount, not small, and you have to also not have too much. If you're too big or too small, you don't qualify. So if you're in the $2 million per year, you probably are outside the range of electric and natural gas. If you're under that, if you're less than, I don't have the number off the top of my head, but if you're in the $10,000, $15,000, $20,000 per month, you probably don't qualify. Okay, you're going to have to be higher than that, because they basically say we're going to have to put our effort where there's a lot of savings potential. We don't want to work on small, very very small facilities, and of course the big facilities have a different program altogether for them.
Okay. In Dr. Sherif's presentation, he will have his contact information available. So if there are additional questions after this webinar, please feel free to reach out to him. He will answer you very kindly. He's very nice in email. So if there are no other questions, we'll go ahead and conclude today. So thank you very much for joining us today. Our next webinar will be on March 21st. Mainstreaming green chemistry and metal finishing operations, again from 11 to noon. Thank you again so much, everyone, for joining us today, and to Dr. Sherif for all your expertise and your time. Thank you so much.
Thank you. It's been my pleasure.
Bye, everyone.